If this doesn't work, we might have to just forego the recording, alas. Okay, so, all right, so what we're gonna do is go through the process of designing a continuously braced beam. Now, the first thing I wanna do is recall the process for analyzing a continuously braced beam. And what we're gonna be spending our time in today from a design standpoint is table 3.2, okay? Now, remember, now this screenshot is actually from the last edition of the manual, but it's still, the pattern's still the same. Remember that the way that table 3-2 is organized, so first off, it's organized based off ZX, right? So if you look, the ZX values all descend. I mean, you can see that. But if you notice, they're kind of like grouped into these chunks, like there might be a group of 5 or a group of 2 and then a group of 7 or what have you. And then within that group, the top row is bolded, okay? The reason why is that, for example, if you look at this top group here, so there's a 24 by 62, 16 by 77, 12 by 96, 10 by 112, 18 by 71. Of these 5, the 24 by 62 is the lightest, okay? So the idea is that what you would do is solve for the required ZX, or solve for the required MP if you're using 50 KSI, go to the table. Let's say for the sake of discussion that you need a ZX of 145, okay? So you go here, well the 18 by 71 has a ZX of 146. You could say, well I'll use that, but instead why don't you just use this one, the 24 by 62, because it's lighter and it still works. So unless otherwise noted, like we'll just go with the bold rows. Sometimes those are referred to as the economy sections because they have an efficient ZX. Now there is sometimes one downside to using the bold row, and that is while it is the lightest, it's also the deepest, okay? And so the deepest might cause a problem from an architectural standpoint. Like let's say the architect says, I need floor beams to resist the loads of this floor, but you only have 18 inches to work with, okay? That's how much room you have. So you can't necessarily go with a 24 by 62 because it won't fit. So those are just some practical considerations that you kind of need to think about. Now the other thing I want to point out is table 3.3. We haven't looked at table 3.3 yet, but table 3.3 is pretty much the same table as 3.2 from an organization standpoint, only instead of organizing by ZX, we're organizing by IX, okay? So this is reporting sections based on their moment of inertia. It's right next to table 3.2. And so what we have, so for example, if we look at this group, we have a group. The top row is bolded because the top row is the lightest within this group, but it's organized based off moment of inertia. So the idea is that you would use table 3-2 for strength requirements and then check deflection, but if you find that deflection's failing or deflection's going to govern your design, then go to table 3.3 and find a section from table 3.3, okay? So we're going to refer to table 3.3 periodically throughout the semester. So to put it in perspective, there are different design aids for continuously braced beams and discretely braced beams. But moments of inertia, this design aid is going to be the same no matter what, okay? So let me explain how continuously braced beam design works, okay? So the first thing that you've got to do, so just to be clear, we're in design mode, okay? So the idea, okay, so let's just sort of conceptualize our problem here. So let's just say I have a beam, let's just, I don't know, make it something like this. And I want to design a beam to resist this load. And I'll just make up some numbers. Let's just do this. Okay, let's say this is our beam design problem. Okay, so I want to design a beam. I want to select a beam to resist these loads. I just made this up. Okay, so the first thing that I need to do is I need to analyze the beam. I need to determine essentially the maximum VU and the maximum MU, right? Okay, but there is a problem, a conceptual riddle with this problem. Okay, I'll just keep it basic and simple. Give me a load that all beams must be strong enough to be able to withstand. Every beam, I don't care what beam it is. Every beam has to be able to withstand this. Their own self-weight, okay? The problem is, I'm in design mode. How heavy is this beam? I have no idea because I haven't picked it yet, right? So the way that we get around that is we have to choose something, okay? We have to pick something. in analysis mode, in the mode where you haven't yet selected a shape, you should assume a value of your self-weight, okay? Common assumptions for steel design are on the order of 50 pounds per foot to 100 pounds per foot. Now, I'll tell you that the more steel design that you do, the better you get at this, okay? So some of this comes with just like experience and time in the industry. If you want some numbers that, you know, you're on a deserted island and you have no basis and you're just trying to come up with something, maybe what I would do is say if you're designing a beam, use 50 pounds per foot. Maybe if you're designing a girder, use 100 pounds per foot. You know, where the beams frame into the girders have a larger tributary area. So that is like an idea, but again, that's kind of basic because there's a lot, you know, there's a lot going into that. I mean, like if you're designing a building that has, you know, significantly high floor loads, like if you were designing a floor system for a library, I'd probably bump those up because libraries carry 150 pounds per square foot. You know, building like this doesn't. So you just got to be engineers about it and use your judgment. There are some engineers that actually don't bother with the self-weight, and because their thought is, well, I'm going to have to analyze the beam anyways, I just don't assume one. I don't recommend that for a couple of reasons. You do have to, I mean, you have to account for a self-weight anyways when you go back and analyze your beam. But if you ignore the self-weight, I think you run the chance of having to iterate too much, and I think it makes the problem longer, so I don't do that. Okay. So the next thing so here's the beam, right? Okay, so we do our structural analysis to get a worst case VU and a worst case MU. And the next thing that we do is we try and figure out what's the worst case, or what's the necessary moment of inertia, okay? Or I put IX required here on the slide. I put here on the board IX min. It's all the same thing, okay? But what we want to do is we want to figure out from step 1, what is the required strength of the beam, and step 2 tells us what's the required stiffness of the beam. What's the required moment of inertia necessary to ensure that we're going to meet deflection requirements, okay? So after these first set of calculations, you're going to, let me go back to this slide. After these first 2 steps, you should have 2 values that you're going to use for design. You're going to have an MU and you're going to have an IX required. Now you're also going to have a VU, but you're not really going to use that for design because you'll just check that later. So you're going to have an MU and you're going to have an IX required. Okay? So the next thing that you're going to do is you're going to use table 3.2 to select an economical shape. Okay? Now because if you're using Fy equals 50 KSI, just look up a section based off Phi and P. Because if we're doing continuously braced beam design, we know that its flexural capacity is going to be MP. So just find a section that meets the MP requirement and use that as a trial shape, okay? Now what we're going to do for that trial shape is also check its moment of inertia. If its moment of inertia is good, then we'll go with it. If its moment of inertia is not good enough, then we're going to go back and select a new shape from table 3.3. So after step 3 and 4, you're going to have a trial shape. And then the last thing that you do is you analyze that trial shape, okay? And by analyze it, you're going to verify that it has adequate flexural capacity, adequate shear capacity, and that it meets deflection requirements. Now when it comes to the moment capacity, at least for continuously braced beams, it's probably only necessary to actually go through the process of checking flexural capacity if the beam is heavier than what you assume. However, I'll say that even if that's not the case, in discretely braced beam design, it becomes more important to analyze because of a particular quirk with some of our design expressions regarding a term called CB. I don't want to get too far into the weeds today because we'll talk about that over the next week or so, but suffice it to say that it is still good practice to go ahead and just check and make sure that the beam works. You do need to check the shear capacity. We're not going to calculate PHBN, we're just going to look it up, and shear capacity is probably not going to be a problem. It shouldn't be a concern with most typical floor beams and buildings. Okay, the next thing is that you do want to check deflection. Now, it technically shouldn't, this one really shouldn't be necessary because if you did all your math correctly, there's no iteration here. So theoretically, there's no reason to do it. However, I think it's a good idea to just go ahead and check to make sure you don't have any calculation errors. I mean, we're talking about beams that are supporting thousands of pounds per foot, and I'm asking you to do one calculation. Do it. You know, it's really not a big deal. Okay. So far, so good. Okay. Now, I have one maybe slight gripe with this manual and this specification. And I'm not the only one. This is a touchy subject in the world of structural engineering, and that is deflection limits in general. Now, if you take a course in concrete design, for example, and you open up the ACI specification for designing concrete structures, the deflection limits are spelled out. I mean, they literally tell you, if here is your condition, your deflection is limited to this. If here is your condition, your deflection is limited to this. And it flat tells you, here are your deflection limits. And so as a structural engineer, it makes it easier for you because you don't have to invent deflection limits. You just look them up in the code. Bless you. And then there's this thing, okay? So if you open this manual up to chapter L, and you don't have to open it up because I have it here on the screen. If you open it up to chapter L, which is the chapter on serviceability, and you read the code and you say, what does the code say about deflections? It says this: deflections in structural members and structural systems shall be limited so as not to impair the serviceability of the structure. And that's it. That's all it says. So what does that mean? Like, do I limit the deflection to L over 360? Do I limit it to 2 inches? What do I do? You know, it's one thing that I kind of wish that AISC would just put some deflection limits in the manual, but I also understand why they don't. The main reason that they don't is that it gives you and your client some flexibility. Like if the client wants the deflection limits to be such and such, then the client can specify that. I'll give you sort of a zany example, but you'll kind of get my point. If you were a structural engineer designing a hospital, the structure for a hospital, the client might go, okay, L over 360 for the building, I don't care, except for this room. I want this room to meet a deflection limit of L over 1,000. Why that room? Because that's where the MRI is. You know what I mean? And maybe you've got some really sensitive equipment in this one room, and the structural or the client's like, we need a very, very stiff floor system for this room because there's very sensitive equipment in there. And so it gives you and the client a little bit of flexibility. I do get that. Okay. Now, fortunately, AISC does sort of recognize this, and the way that they get around this is through what are called design guides. Okay. Now, on the side, one thing I'll mention is that as students, you all had to start an AISC account to get the manual, right? Okay. Well, as students, you also have access to download these design guides for free. Okay. These design guides can get pretty expensive. Like to buy these things, they're thousands of dollars. Okay. Like to buy them all. Okay. And there's a series of them. And the idea is that the design guide covers. Here's sort of the idea. You all take an undergraduate course in steel design and you cover the basic components of steel design. And then you get out there and you've got a problem that we didn't talk about in class, like torsion or floor vibrations or whatever, right? And so the idea is that these design guides will help fill in the gaps. And there's a lot of really good design examples and things like that in there. Design Guide 3 is the one on serviceability considerations. And a lot of structural engineers tend to just refer to that. And so, for example, if you're looking at plastered ceilings, for example, for roof members, then the maximum deflection is L over 360, right? If you're looking at a frame and you're talking about its horizontal movement, its deflection limit is H over 500 under a 10-year wind or something like that, okay? So it does help you out really straightforwardly. And I want to be clear though, for the purposes of this class, I'm just going to give you the deflection limits, pretty similar maybe to what a client would do. I'm just going to tell you, I want you to design this beam for L over 600 or L over 360 or what have you. So I'm just telling you that I'm going to give you the numbers, but that's me getting off the soapbox. Okay. Okay. So now we're going to design a beam. Let's design this beam. I'm keeping the beam pretty simple. It's a simply supported beam subjected to a uniformly distributed load and a point load. Okay. The point load is 40 kips and it's right at midspan. And we're going to design this beam to ensure that it not only meets strength requirements, but it also meets a deflection limit of L over 600. That's a little bit of a stringent deflection limit, so just throwing that out there. Now, this dead load does not include the beam self-weight, okay? So we would say that this dead load is superimposed, right? So the dead load of the beam or the self-weight of the beam, and then the dead load on top of that weight. So we call that superimposed. So if you hear me use the term superimposed, that's what that means. Make this a little bit bigger. Okay. Okay. All right. Good to go? All right. So the first thing we need to do is we need to analyze this beam, okay? So ultimately what we're going to try and do is determine VU and MU, okay? So we're going to use these lovely little design aids in the manual, okay? So let's go through this, okay? So all right, so okay, so we're going to analyze the beam, okay? So first off, for the dead load, okay? So we're given a dead load of 1.2 kips per foot, and we're given that we should assume that the self-weight of the beam weighs 50 pounds per foot. Like, that's what we should assume. So 50 pounds per foot or that. So therefore, the total self-weight here is that. Now, here's something I'm going to do. I'm going to put a big old assumed right here. And I'm going to jump back to that assumed note a little bit later to see whether or not this assumption is valid or we need to correct this. Okay? Now, the beam is 35 feet long. Okay? Okay, so using these, I want to determine a worst case dead load shear and a worst case dead load moment. Okay, so help me out. What are my expressions going to be? Like, what equations am I going to use? I have a simply supported beam subjected to a uniformly distributed load. So how am I going to calculate the dead load shear and the dead load moment? What am I going to use? We've already used them in class before.
Case 1.
Case 1. And so the dead load shear is going to be what?
WL over 2.
There we go. And this one's going to be WL squared over 8, right? That's supposed to be D plus O. Okay. So, it's 35 feet. With me so far? So somebody give me this one and this one. Everybody's sleepy this Monday morning, I guess. 21.88 for speed. And this one, I'll go ahead and give you this one. I'll be gentle. You can check me if I'm right. Okay. All right. Now, I want everybody to watch up here. Okay. Okay, so here's the beam, okay? Now for dead load, we had a distributed load across the beam, right? Now for live load, we have this, right? Live load in this case is 40 kips. Now, somebody tell me what they're going to do to analyze this beam. What are you going to do? I mean, we've used our case 1 expressions. We use these expressions for dead load. So what are we going to do for live load?
Use case 7.
Okay. That is the correct answer. Okay. Now I want eyes up here. Okay. Because somebody in here is going to do this. Somebody in here is going to say, here's what I'll do. I'm going to say, okay, here's the beam. And I'm going to take this 40 kips and I'm just going to turn it into a distributed load. And we'll say that it's 40 over 35. Somebody in here is going to do that, okay? And when you're thinking about doing that, okay, I want you to take your hand, stick it like this, okay? Then I want you to do that. Knock the pencil out of your hand. Don't do that. That's wrong. No. Okay? And let me explain why. Okay? This problem is a beam. This problem has a beam with 40,000 pounds lumped right in the middle. Okay? This is a beam design problem, ladies and gentlemen. We are designing this to withstand bending. Now, which do you think is a worst case scenario? Sticking 40,000 pounds right in the middle or spreading it out over the length of the beam? The middle, right? So if you do this and do that and turn it into that, you are producing an unsafe design, okay? So again, hand, no. Don't do that. We're going to handle this accordingly, or we're going to handle it with case 7. And so, what is VL and ML? What is VL? P over 2. And this is PL over 4, right? Do y'all know where these equations are coming from, by the way? I mean, let's just make sure we're comfortable with that, right? So if you have a simply supported beam, right, and you put P right there, right, that means that this reaction is P over 2, this reaction is P over 2, right? So what does the shear diagram look like? Shear diagram, you go up P over 2, over, down, over, up. So that's P over 2, that's minus P over 2. Then remind me, how do we draw a moment diagram? We integrate the shear diagram, right? So what's the area of that little rectangle? P over 2 times L over 2? Right? Go up, down. Remember that? That's where these equations are coming from, right? It's just doing them symbolically, okay? All right. I wanted you to know that all that stuff you learned last semester was worth something. 40 kips over 2, 20 kips. So 40 over 4 is 10, 350. Right? And so from these, we determine a factored load. excuse me, so 1.2 times 191.41 plus 1.6 times 350. So we get VU equals and MU equals. Just to make sure everybody's awake, somebody give me a VU. $58.26. Do I have a second? I heard a yep. And then MU is what?
789.7.
Okay. All right. And I'll tell you, that's actually kind of the longest step in the whole problem, is the first step. Okay? Just making sure that we've got the moments and shears computed appropriately. So let me erase all this. So I'm going to write this on the board so that we have it. VU is 58.26 kips. Okay. Now, the only other thing I'm going to add here is that these are based on a self-weight of 50 pounds per foot. Would you agree? Let's just keep that in the back of our heads. We might refer to that later. Spoiler alert, we will. Okay. All right, so this is analyzing the beam, but we're not done yet because we also have a deflection limit. Let's look at a required IX. So, if you recall, during our last example that we did in class, we actually found that the deflections govern the design, which is very possible, okay? Especially on a problem like this where the deflection limits are kind of tight, okay? So let's look at our required moment of inertia for this problem, okay? So we know two things, okay? First thing that we know is the deflection limit. And the deflection limit is L over 600. Right? We were given that, right? So we can go ahead and compute that right here. Now, 35 over 600 is going to give you an answer in feet. This is something we need in inches. So when we chug this out, what do we get? 35 times 12 over 600. 0.7. 0.7 inches. Okay? Now, what is our maximum live load deflection going to be? Better yet, how do we compute the maximum live load deflection for this beam? There, hold on. You're doing this. Hold on, wait.
Nope.
Nope.
PL cubed over, is it, I guess 48 EI?
There we go. This is our expression for maximum deflection, right? So again, it's very tempting to do this, but no, right? Again, the same thing I said about strength is the same thing I said about deflection. Which do you think is going to cause the beam to deflect more? Spreading the load out or lumping it in the middle? Lumping it in the middle, right? So, for this beam, what do we know? We know that PL is what? 40 kips. L is 35 feet. And E is what? There we go. It's I we don't know. Okay, so let me show you how I'm going to handle this. All right. First thing I'm going to do is this. Let's just write out our expression for the deflection. Okay, so how are we going to do this? So PL cubed over 48 EI. I'm leaving this as a symbol because I don't know what it is yet.
Do we need to include that unit conversion?
There you go. I was wanting to make sure somebody remembered it. Yes, we do need to include our conversion factor. Because when we solve for this, we want to solve for it in inches to the fourth, right? So if we don't include a conversion factor, we're going to get some weird units for that, okay? So how am I going to solve for Ix? How am I going to do that? Well, this is my limit, and this is what my deflection is. Why don't I just set these two equal to one another, right? So I'll set these two equal to one another. So, how do I solve for Ix? What do I do? So tell me what to do. How do I solve for Ix?
Switch it.
Flip them, right? So therefore, we'll say Ix required. And what do we get for Ix required?
3,041.38.
Say it again.
3,041.38.
We'll call it that. Okay. So now we've got another thing to add to our design list. Okay, so where are we at in this problem? Well, we have not yet selected a beam, but now we've got some parameters for which to go off of. We need to select a beam that can at least resist this much moment and has at least this much stiffness, okay? So, let's walk through that, okay? So, step 3, let's do some design. So the first thing we're going to do is select select a trial shape based on MU, okay? Let's look at this one first. Remember, I'm not really going to worry about the shear. The shear, it's going to have enough capacity. I'm really not worried about that. But let's pick a trial shape based off MU. And what I'll say is that for a continuously braced beam, phi mn is just phi mp. Okay, so somebody help me out. Let's go to table 3.2, okay, and just walk through with me on this. Let's just find the lightest W shape that we can that has at least this much flexural capacity. Let's just look at phi mn for right now. So, anybody have a trial shape that'll work? Again, we're going to ignore the moment of inertia for right now. Let's just look at phi mp. So does anybody have a trial shape that's going to work? Okay, 18 by 97. What's the phi mp for that? Okay, let me ask a question. Is that a bold row? So, what's the bold row that's associated with that? So why would we pick the bold row over that one? It's lighter, right? It's lighter, it costs less. So we'll say try a W24 by 84. Now you're picking that because it has a phi mp of 840. So, does it have enough flexural capacity? Yes. For the sake of discussion, does it have enough shear capacity? What's its VBN? It's on the right end of the table. Say it again. 340 kips. Is that enough to withstand that? Oh yeah. But here's the problem. What is its moment of inertia?
2,370.
Or, that's not kip. Is that going to work? No. So we have selected a section based off strength. We found that it's not going to work. It's not stiff enough. It's going to deflect too much. It won't fail, but it'll deflect too much. So now, we're going to abandon table 3.2 for now and select the trial shape. Based on IX. So now we're going to go to table 3.3, okay? And help me out. Find me the lightest shape that you can that has a moment of inertia of at least 3,041.
By 158.
18 by 158? Which are you in table? Are you in the IX or the IY table?
X.
What value did you get? Yours sounds better. 30 by 90? That sounds a lot better.
30 by 30.
He was just looking at the IX, he wasn't looking at the bold number.
Oh, yeah.
This is the bold number.
Yeah.
Oh,
The bold one is a 30 by 90.
Yeah, so we're going to go with the, it's a lot cheaper, right? Yeah, we're always going to pull the bold rows unless there's some depth limitation, okay? So a 30 by 90 has a moment of inertia of, what, 3610? But let's not become a dog chasing its tail. Is this going to work from a strength standpoint? What is the phi mp for a 30 by 90? Say it again.
1060.
1060. Now, is this worth analyzing? I think so, right? I think this is so, this is so. So let's try a W30 by 90. Now, I'm saying try a W30 by 90. Why can't I just say it's the answer right now?
Because you have to verify.
Why do I have to verify that? Bless you. Say that again. And what did I assume? 50 pounds per foot, right? What is the self weight of a 30 by 90? 90 pounds per foot, right? So the 30 by 90 is heavier than what I guessed, right? So because it's heavier, these values are off. Now they're not off by a lot, but they are off, right? So what I need to do is I need to redo my numbers, right? So I'm going to, since we're running short on time, I'm going to speed through this a little bit, but let me kind of show you how this is going to work, okay? So now we're going to analyze the W30 by 90. So we have a dead load of 1.2 kips per foot, but now we have a self weight of 90 pounds per foot, or 0.09. So the beam is a tad heavier, okay? So what that means is that I'm going to need to redo these. And I'm going to go ahead and give you these because we are running short on time. So when you update these, remember L in this case is 35 feet. So when you update these, you get 22.58 and you get 197.53. And remember, we do still have VL is 20 kips and ML is 350. So with these, what we can do is compute new shears and new moments. And I'll go ahead and give you these as well. This one comes out to be 59.09 and 197. And 197.3. Wait. Oh, I was writing down the wrong one. This is 797.0. Whoops. I was writing down the same one over again. This is 797.0. So a little bit bigger than what we assumed. A little bit. Not a lot, but enough that I do think it's worth a check. Now, when you look up the PMP for the W30 by 90, again, we get 1060. And then the PVN for the W30 by 90, again, it's pretty big. It's like 374. So again, are we good from a capacity standpoint? I mean, you tell me, are we good?
Yeah.
Yeah. The only thing left to do is maybe check deflections. So remember we had a limit of 0.7 inches. Then we have a maximum deflection of PL cubed over 48 EI. Well, now we actually have an I value, so we can compute this out. And then now we're going to use the actual I value of 3610. This is 40 kips, 35 to the third, and then don't forget your conversion factor. And then, so I'm just recomputing the deflection, but now that I actually have a moment of inertia for the shape that I've tried, I can actually check it. And when you chug this out, you get 0.590. So you tell me, does the W30/90 work for this beam? Yes. And this is in fact the lightest shape I think we can find for these loads. So I would say use a W30/90. That's the answer. And if you want, you can say the performance ratio for moments, if you chug it out, is like 0.752. The performance ratio for shear is 0.158. Again, W shapes tend to just have a phenomenal amount of shear capacity in beam scenarios. And then the performance ratio for deflections is 0.843. Now, note that this is the highest one. Deflection is what governed. But we kind of knew that was going to happen before we even did all this math, because we tried table 3.2 and it didn't work. So we had to go to table 3.3 to pick a shape, right? We tried to pick one off strength, it didn't work, so now we picked one off deflection, and then by golly gosh gee, we get the largest value out of deflection for our 3 performance ratios. So, I mean, you know, what do you expect? Okay, I will show you real quick about the homework, because I know you all are trying to leave. So this one I made a lot easier because it's all just distributed load, so just WL squared over 8. The only load on the beam besides the self weight is the live load, so which is not uncommon, okay? And it's a much more loose deflection limit, so maybe deflections govern, maybe they don't. So we'll see how you do with this. That's all I got, everybody. I'm going to stop the recording, pull up the code, and I will see you all on Wednesday.